part 2 of the derivation of the constant strain triangular element, stiffness matrix and equations. So we are working in the XY plane. We were looking at a triangular element, I, J, M. We go in the counterclockwise direction. Each node had 2 degrees of freedom. So we were looking at a D that is 6 by 1. And we expressed the displacement using Psi, where Psi is equal to U of X and Y and V of X and Y. So this is equal to 1 X Y 0 0 0 0 0 0 1 X Y multiplied by 6 parameters that we were solving for: A1, A2, A3, A4, A5, and A6. And in order to obtain A's, we substitute in the coordinates of the nodal points I, J, M. So we had here XI, YI, XJ, YJ, and XM, YM. So when we did that, in order to solve for A, we were able to express it in matrix form. I got a UI, a UJ, and a UM that was equal to 1 XI, YI, 1 XJ, YJ, 1 XM, YM multiplied by A1, A2, and A3. We refer to this matrix as X. And we said we can solve if this matrix is A and this is U. I can solve for A if I find the inverse of X, then I can multiply it by U. And we said this inverse of X is equal to 1 divided by 2A, where 2A is the determinant of the matrix X multiplied by the cofactor matrix, where we had alpha I, alpha J, alpha M, beta I, beta J, beta M, gamma I, gamma J, and gamma M. And this is where we stopped. Now this 2A, knowing the matrix X, may be written as Xi multiplied by Yj minus Ym plus Xj times Ym minus Yi plus Xm Y I minus Yj. And then we call it 2A because this is twice the area of our triangular element. If we evaluate the cofactor matrix elements, I will get an alpha I that is equal to Xj Ym minus Yj Xm, and alpha J that is equal to Xm Yi minus Ym Xi, and alpha M that is equal to Xi Yi minus Yi Xj, a beta I that is equal to Is this too small or acceptable? So beta I is equal to Yj minus Ym, beta J equal to Ym minus Yi, and beta M equal to Yi minus Yj. Gamma I is equal to Xm minus Xj, gamma J equal to Xi minus Xm, and gamma M equal to Xj minus Xi. So these are the 9 elements that we're going to be using for the inverse of X. So I can now evaluate A1, A2, and A3 as equal to 1 over 2A multiplied by alpha I, alpha J, alpha M, beta I, beta J, beta M, gamma I, gamma J, gamma M, multiplied by UI, UJ, and UM. Now, similarly, we may express VI, VJ, and VM as equal to 1 XI, YI, 1 XJ, YJ, 1 XM, and YM multiplied by A4, A5, and A6. And we can solve for A4, A5, and A6. This is uppercase A, I'm sorry. As equal to also 1 over 2A. So the inverse of the matrix A multiplied by alpha I, alpha J, alpha M, beta I, beta J, beta M, gamma I, gamma J, and gamma M, multiplied by VI, VJ, and VM. And we can express U as equal to 1xy multiplied by A1, A2, and A3 or you can see that U is equal to 1 over 2A times 1xy multiplied by, for A1, A2, A3, I will put alpha I, alpha J, alpha M, beta I, beta J, beta M, gamma I, gamma J, gamma M, multiplied by UI, UJ, and UM. And U then is equal to 1 over 2A multiplied by alpha I plus beta I times X plus gamma I times Y. So this is the first term. And then a second term would be alpha J plus beta J X plus gamma J Y. And then a third term would be alpha M beta plus beta M X plus gamma M Y. So I have here three terms multiplied by UI, UJ, and UM. I want to remind you, we were able to relate the displacement function to nodal displacement using shape functions. So these are then the shape functions corresponding to degree of freedom 1, 2, and 3, or I, J, and M. So I can write here Ni is equal to 1 over 2A, and I'm going to have here my first term multiplied by alpha I plus beta IX plus gamma IY. I have an Nj that is equal to 1 over 2A times alpha J plus beta Jx plus gamma Jy. And I have an Nm that is equal to 1 over 2A multiplied by alpha M plus beta mx plus gamma my. This would also be true for the v. I can express v as equal to 1 over 2a multiplied by ni, nj, and nm multiplied by vi, vj, and vm. If I want to express the displacement psi in matrix form, where psi is equal to u of x and y and v of x and y, I can write it as equal to ni 0, nj 0, nm 0, and here I have 0, ni 0, nj 0, nm, and here I'm going to have my displacement, nodal displacements in order. So I'm going to have ui, vi, uj, vj, um, and vm. We're going to call n, make n function here, matrix is equal to, this is a 2 by 6. I have ni 0, nj 0, nm, and 0, 0, ni 0, nj 0, nm. Now, just to refresh your memory, Ni represents the shape of the variable u plotted over the surface for ui equal 1 and all other degrees of freedom equal to 0. Question.
So when you have the shape function, the 1 over 2a is in the shape function itself, so it's, are you saying you multiply this technically twice? You have the 1 over 2a on the outside of that as well. Sure. That was
No, I think this is a mistake, and if I use ni, ng, and nm, there is no 1 over 2. Thank you, Andre. Now, if I have what I'm saying here, if I do have u of xi and yi, that would be equal to a ui. Correct. If all the other degrees of freedom are equal to 0, Ni is going to be equal to 1, and Nj equal to 0, and Nm equal to 0. If you imagine, if I plot that on, if this is like X, this is Y, and we have this triangular element, something like this, where this is I, this is J, and this is M. If we have a value, so I'm going to be representing here, if this is like Ni, this Ni is going to be equal to 1 at I, and is equal to 0 at J and M. So the function Ni is a function of X and Y. So it's going to be represented by a surface. This surface along this edge is going to start here at 1 and then goes to 0. And here, should have used a different color. And here also along the IM face is going to start from 1 and go to 0. And here is going to be equal to 0 only along the JM face. So this green function represents Ni. It is also important to recall, one of the things we learned about shape functions is that at any point Ni plus Nj plus Nm should be equal to 1. For all X and Y locations on the surface of the element. On surface of the element. Why is this important, or where did this come from? Our shape functions should allow for rigid body motion. Rigid body motion. So if we get a uniform translation due to rigid body motion, then they should all be added together to 1. The shape functions are also going to be used to determine equivalent nodal forces for body and distributed loads. So this is another good use for the shape function. And as I mentioned, for completeness requirement, the element must be able to translate uniformly in either the X or Y, as well as rotate uniformly. And when I say here rigid body motion, I mean that there is no stress or strain within the element. Zero stress, zero strain. So now we are ready to move to step 3, where we're going to look at the strain displacement relationship. And then we're also going to look at stress-strain relationship and also relate the stress to displacement. But let's start here with the strain displacement relationship. The strain epsilon or the strain tensor may be described by epsilon x epsilon y and gamma xy. This is equal to the partial derivative of u with respect to x for epsilon x. For epsilon y would be dv by dy. And for gamma xy, we're going to get du by dy plus dv by dx. Now, having expressed u and v using displacement function, we had u equal to a1 plus a2x plus a3y, and v equals to a4 plus a5x plus a6y. I can say that epsilon x, epsilon y, gamma xy may be expressed as equal to, if I take the partial derivative with respect to x, I get 2. If I take the partial derivative with respect to y, I get a6. And if I take the partial derivative of u with respect to y, I get an a3. And partial derivative of v with respect to x, I get an a5. If I look at the partial derivative of u with respect to x, and by the way, we're going to use a notation. We can write this as u, and then subscripts, comma, x. This is like taking the partial derivative with respect to x of u, and if I take u expressed using shape functions, I can write it as ni ui plus nj uj plus nm right? So we can write u comma x is equal to, if I apply that operator, now the nodal displacements are constant. So if I apply the partial derivative to the shape functions, I'm going to get ni comma x multiplied by ui plus nj comma x multiplied by uj plus nm comma x multiplied by um, where the comma x is to, like, say, partial derivative of that shape function with respect to x. So for example, we had here the ni as equal to 1 over 2a multiplied by alpha I plus beta I x plus gamma I y, right? So if I take the partial derivative ni x, that would be 1 over 2a, and I'm taking, this is a constant, taking the partial derivative here with respect to x, I will only be left with beta I. So if I do here this partial derivative with respect to x of alpha I plus beta I x plus gamma I y, I will end up getting ny comma x equal to only beta I divided by 2a. Similarly, we can show that nj comma x is equal to beta j over 2a, and nm comma x is equal to beta m over 2a. if I go back to u of x, sorry, u comma x, u comma x, I can write it as, I take 1 over 2a as a common factor, because I have all these terms have 1 over 2a. And then I'm going to have beta I multiplied by ui plus beta j multiplied by uj plus beta m multiplied by um. Similarly, we have v comma y equal to 1 over 2a multiplied by, we're going to end up getting gamma I vi plus gamma j vj plus gamma m vm. And for u comma y plus v comma x, I'm going to get 1 over 2a multiplied by beta I vi plus beta j vj plus beta m vm plus gamma I ui plus gamma j uj plus gamma m um. Now, I'm going to substitute here in epsilon. So this epsilon is this 3 by 1. I'm going to say this is equal to, and I have epsilon x, epsilon y, gamma xy here expressed in terms of the partial derivatives. And looking here at the partial derivatives, I can take 1 over 2a as a common factor. Then I'm going to have a matrix that is a 3 by 6. Multiplied by the nodal displacement, which is 6 by 1. So I'm going to have here ui, vi, uj, vj, and um, vm. So we have here a 6 by 1, and here I have a 3 by 6. So this is how I get up with the 3 by 1. Now this 3 by x, we're going to get the coefficients from here. So I have here a beta I, then I have a 0, then I have a beta j, then I have a 0, then I have a beta m, then I have a 0. For v, I get a 0, then a gamma I, then a 0, then a gamma j, then a 0, and a gamma m. For the third row, I have a contribution for both ui and vi. So I'm going to get a gamma I, beta I, gamma j, beta j, and gamma m, beta m. Now, if I look at this term and call it bi, and this term, call it bj, and this term, call it bm, such that bi is equal to beta I, 0, 0, gamma I, beta I. So we have a 3 by 2. Likewise, Bj equal to beta j 0, 0, gamma j beta j. And finally, Bm equal to beta m 0, 0, gamma m, and beta m. I can then express a function, a matrix B that is 3 by 6 using partition matrices as Bi, Bj, and Bm. And I can express a relationship I think I would want to put here also 1/2a. So then I can say that epsilon may be expressed by B times D. And here is B, 3 by 6, using the partition matrices Bi, Bj, and Bm. So this is our strain displacement relationship that we were looking for. Now we have stress strain relationship. Expressed as sigma equal to D multiplied by epsilon. And remember that D was different for plane stress than for plane strain, right? So we had a D for like plane stress. We had the D that was equal to E divided by 1 minus nu squared multiplied by 1 nu 0, 0, 1 nu, and then 0, 0, 1 minus nu over 2. Versus for plane strain, the D was equal to E divided by 1 plus nu multiplied by 1 minus 2 nu. And we had the 3 by 3 here was 1 minus nu. We had nu, we had a 0. Then we had nu, 1 minus nu, 0, 0, 0, and 1 minus 2 nu over 2. We derived these earlier. Now, if I want to look at a stress displacement relationship, I will simply substitute for epsilon in this equation. So I will come here and say then the stress sigma is equal to D multiplied by B times D. So I'm relating the stress to the nodal displacements. Now we are ready to move to step number 4 in our process to derive the stiffness matrix and equations. And this is a plane element, so we're going to use the minimum potential energy approach, right? So we want to find an expression for pi p in terms of the nodal displacements. So we want to write pi p as some function of ui, vi, uj, vj, and vm. So this is our goal. And the potential energy was equal to the strain energy U plus the potential energy of external forces gamma. When I'm looking at a plane element, the external forces could be expressed in terms of concentrated loads, body forces, and surface loads. So instead of having one gamma, I'm going to put a gamma B for body loads, a gamma P for concentrated loads, and a gamma S for surface loads. I'm going to start here by the strain energy, U. U may be expressed by half the triple integral over the volume of epsilon transpose times sigma dV. For body forces, potential energy, gamma B. Gamma B is equal to minus the triple integral over the volume now these body forces will be expressed in terms of x, and x is a force per unit volume. Okay, so I'm going to multiply this by the displacement function psi and the transpose for the matrices to work out, and we're taking the triple integral over the volume. So this x represents the body forces. Units are force per volume, as in gravity, for example. And psi is the displacement function. Next, we're looking here at the concentrated loads. Potential energy. This is gamma P. This gamma P may be expressed by minus the corresponding displacement transpose here, or the nodal displacements, multiplied by P applied at the node, right? So D is the nodal displacements, and P are the concentrated nodal loads. And finally, we have here the surface load or surface traction potential energy. Gamma sub S, where this gamma sub S is equal to minus the double integral over the surface of the displacement function C evaluated on that surface, and I take the transpose, multiplied by the traction applied on that surface, ds, where this ts is surface traction, cs is the displacements on the surface. So in order to evaluate CS, if psi expressed in terms of shape functions, I will evaluate my shape functions on that surface and multiply them by the nodal displacements. So CS is equal to NS times D, of course, where C was expressed using N times D. Now, we were able to express the strain in terms of displacement by epsilon equal B times D, and the stress was expressed also in terms of nodal displacement as D times B times D. So if I come here at my equation for pi p, I would say pi p is equal to 1/2 the triple integral over the volume. For epsilon transpose, I will have T transpose times B transpose. And then for sigma, I'm going to have D times B multiplied by D dV, right? Minus the triple integral for gamma B over the volume of psi times x. For psi, I'm going to use N and it's a transpose, right? So I'm going to actually put the D here, transpose times N transpose multiplied by x dV. Then for the concentrated loads, I'm going to have minus D transpose multiplied by P. And then finally for gamma S, I'm going to use a minus the double integral over the surface of CS transpose. I'm going to put here the D transpose times NS transpose multiplied by TS DS. Okay, let's simplify a bit. Pi p is equal to now the nodal displacements may be pulled out so I can get half d transpose times the triple integral over the volume of b transpose times d times b. Yeah, I'm going to put dv and then multiply by d because d also is constant, nodal displacements. Minus, again, we're going to pull here the d transpose times the triple integral over the volume of n transpose times x dv minus d transpose times p minus d transpose double integral over the surface of ns transpose ts times ds. So we clearly see here the d transpose. So we can write, let me write it here, pi p as equal to 1/2 d transpose times the triple integral over the volume of b transpose times d times b dv times d minus, I have here the d transpose. I'm going to take this as a common factor and I'm going to multiply it with an f, where this f is equal to the triple integral over the volume of n t times x plus p plus the double integral over the surface of ns transpose times ts. Now, if I take the partial derivative of d pi p with respect to the d's, I will get here the triple integral over the volume of b transpose times d times b dv multiplied by d minus f is equal to 0. Which if we look at this term here would be k, and I have here d, and I can move f to the other side and say this is equal to f. So therefore, the element stiffness matrix K may be expressed as the triple integer over the volume of B transpose times D times B dV What is the order of K? So this B was 6 by 2. B is a 3 by 6. But we have it transposed, right? So we'll be looking at a 6 by 3, 3 by 3, 3 by 6. So K is a 6 by 6. Now, if my triangular element has a constant thickness, so for constant thickness T, K may be written as T times the double integral over the area. I have here B transpose still D times B D A now. For the constant strain triangular element, K will become equal to T times A multiplied by B transpose times D times B and the strain energy U that we were looking at, U, is equal to 1/2 D transpose times K times D. So if you're interested in finding the strain energy, this is how we would find it. Now, we had an expression for 2A using the ordinates of I, J, and M. So we can find this A using that expression. Now, this K 6 by 6 is going to be equal to can write it in terms of partition matrices. K II, K ij, KIM as it relates to the degrees of freedom, right? KJI, KJJ, KJM, KMI, KMJ, and KMM, where, for example, a KIJ, which is a 2 by 2, is equal to BI transpose multiplied by D multiplied by Bj, so see here Ij, I get here the I and the J, multiplied by T times A. So we have the T by A here. So we were able to, since the integrand here is not a function of X and Y, we were able to write it as TA. Okay, so A, just to redo it here, is equal to 1/2 multiplied by Xi times Yj minus Ym plus Xj multiplied by Ym minus Yi plus Xm multiplied by Yi minus Yj. Right? That's the answer. In most cases, we are going to express the element and the element coordinates with respect to the global coordinates, right? So we'll be using the global coordinates, X and Y, and expressing the element stiffness matrix using global coordinates. Should there be any reason that your element ordinates are expressed with respect to some other direction or local ordinates, X prime, that makes an angle theta with the X, and of course a Y prime perpendicular to it. So Y prime also makes the same angle theta with Y. Then we are going to need a transformation matrix. Okay, but no big deal. If that's the case, then so if the local axis Y prime, I'm sorry, X prime, Y prime are not parallel to the global axis, X and Y, then we'll be using T. And this T is based on the 6 degrees of freedom, or corresponding to the 6 degrees of freedom. So we have like UI, VI, UJ, VJ, and UM, VM, right? And if I break this as a 6 by 6, we organize it here like this. We'll find that we'll use the transformation matrix CS minus SC corresponding to UI and VI. Then everything else here in the first 2 rows would be zeros. In the second corresponding to UJ and VJ, here I'm gonna get a CS minus S and C, and then zeros everywhere else. And finally, I'm going to get the CS minus SC corresponding to UMVM, and everywhere else is a 0. Now, your global stiffness matrix for the element K may then be expressed as T transpose times K prime multiplied by T. Now, step number 5 would be to assemble the global stiffness equations and matrix. So basically, you're gonna put together this uppercase K, which is equal to the sigma from E equal 1 to N, where N is the number of elements of all, sorry.
Excuse me, so K prime stands for what?
The element stiffness matrix with respect to the local axis, X prime, y prime. So here I am putting k, and please note that these k's are not the primes. In order to do the summation, I'd be with respect to the global axis. So k for all the elements E, and I can also write an equation, the matrix F for the external nodal forces. This is equal to sigma from E equal 1 to n of all the elements of all the elements, external forces of the elements. And then I can write my equation, my global stiffness equation as F equal to this uppercase K multiplied by D as before. So this is step 5. Step number 6 would be to apply boundary conditions and solve for D. So we find the nodal displacement. And then step number 7 would be to solve for the stress sigma using D. And this stress would be for each element. So we had an equation that relates the stress to the nodal displacement. So I can use the nodal displacement for each element to find the stress per element.